So hello, everybody. I see that more and more people are joining. So I think we're good to start. So welcome to today's webinar. My name is Clara Zolster-Skachanova, and I'm the manager of the market development team at SCHWAIGER. So today I will be your host for the webinar on the LiveFront project, which is an EU-funded project. And today we have the pleasure to announce the launch of two databases, leakage size database and concentration database, which will be the focus of today's webinar. So before we actually start, I would like to just give you some basic technical announcements. Just in case you have any difficulties with the sound, you can click in the toolbar on the audio settings to check your speakers so that you can hear us. You can also join the discussion by clicking on the Q&A button. So you can type your question at any time during the webinar, and please make sure you indicate which speaker the question is addressed to. We will be taking the questions at the end of the webinar after all the presentations. Also, if you have any technical questions, if you, for example, cannot see the presentation or if the slides are not changing, this can of course happen. We are relying on technology, so that happens sometimes. Please let us know so that we can fix it as soon as possible. So without further ado, I would like to start this webinar with an overview. So you can see here on the slide the presenters and the topics. So my colleague here, Pauline, will present you about the LiveFront project, what the project is about, what the objectives are, and also how you can join and contribute to the project's objectives. And then Daniel Colbourne, who is our next presenter, will talk about, we'll talk about the Europe's largest leakage size database, which we're launching today. So this is the main topic, of course. And then we'll have contributions from LAURE and MELJAC from NIBE and Werner SCHWAIGER from AHT about their perspectives on this database, which they have also contributed to as partners of the LiveFront project. So they will share their experiences, their reasons for joining this effort, and also how this can serve the industry overall to increase the uptake of hydrocarbon-based technologies. So with this, I would like to hand over to my colleague, Pauline. Pauline is SCHWAIGER's project coordinator. She's managing the LiveFront project, and she has a long experience in managing projects. She joined SCHWAIGER just recently, but she's already fully on board with the LiveFront project. So Pauline, the floor is yours for the project overview.
Thank you, Clara, and a very warm welcome from my side as well. So I will briefly introduce you to the LiveFront project. So FRONT actually stands for Flammable Refrigerant Options for Natural Technologies, and the project focuses on improved standards and project design for their safe use. And it's, as Clara mentioned, it's co-funded under LIFE. The LIFE program is the EU's financial instrument supporting environmental, nature conservation, and climate action projects. So the project is structured in 7 actions that run in parallel and that actually build on each other. More information is of course available on our website, livefront.eu. The project started in June 2017 and we will end next year in June as well. So SCHWAIGER is coordinating that project together with a set of partners, among them ECOS, HEAT, and industry partners such as AHT, AIT Deutschland, and NIBE. The project aims to remove barriers posed by standards for flammable refrigerants in HVAC and refrigeration, And there are 7 key objectives. The first one is to support the EU and international standardization process for flammable refrigerants. This is done through a review of existing and drafting of new standards requirements and involvement in standardization actions and bodies. The second objective is to reduce safety risks from improved system design for air conditioning, refrigeration, and heat pump applications using flammable refrigerants. And this is done through theoretical and applied research. The third objective is to increase the availability of alternatives to replace HFCs. The project also focuses on engaging in technology capacity building for EU equipment manufacturers using or planning to use flammable refrigerants, and this is done through a standards action group, about which I will talk a bit later in my presentation. This is also done through sector-specific best practice manuals. The project also focuses on removing non-technological knowledge barriers across relevant European groups. And this is done through general awareness raising activities and stakeholder dialogues, such as today's webinar. The other goal is also to improve Europe's competitiveness for RACHP equipment using non-fluorinated refrigerant alternatives, and to support an effective and timely achievement of the EU 2030 climate targets, namely through the F-gas regulation, Eco-Design Directive, Renewable Energies Directive, as well as other legislative instruments for the reduction of fluorinated gases, the use of renewable energies, the reduction of energy consumption. The Standards Action Group that I mentioned earlier is a creation of the LIFERN project, and it's actually a voluntary group that currently has 30 members that are all interested in the development of EU and international standards on product, environmental or safety requirements for flammable refrigerants. The main expectation from the participants are to join in an online working group, which is currently set up, where the stakeholders can exchange valuable input that are really important for the crucial stages and deliverables of the project itself. They can also contribute to draft requirements for standards. The output that is expected from this work is to bring high replicability and transferability of project results into members' business activities via dissemination of best practice methods. So it's possible to still join the Standards Action Group. So you can do so via our website, as you can see here in the Get Involved section. Moving on to the project actions, there are 4 big set of actions as part of the project. The first one is the literature review and market study that entails mapping and analyzing the current state of relevant European and international standards, and a market study that is available already on our website that is mapping available technology and product groups that are using hydrocarbon refrigerants. Also their expected future availability and all the impacts of standards on such market development. And as I said, this study is available on our website. The second big activity is the leak analysis. And this is actually the focus of today's webinar, during which we conducted a field study of types, cause, size of leaks, and the online leak hole size and leak simulation database that is that we will present today. This activity also includes a laboratory study of leak mass flow rates and gas concentration measurement. The third activity of the project is improved product safety design and quantitative risk assessment. This includes the redesign of prototype models according to the best practice principles, as well as a risk assessment to identify improvements in risk reduction associated with the implementation of new mitigation measures, and sensitivity, especially concerning incremental increase in charge sizes. The fourth, last but not least, activity is about standardization action and capacity building. So as I mentioned, there is the standards action group that is already up and running. And there is also a very important activities concerning the draft requirements for flammable refrigerant standards. So that's it for my presentation. Thank you very much for your attention.
Thank you very much, Pauline. So indeed, the project is now in the second year, and next year we will be wrapping it up, but this is just the beginning, I would say. And it's a very important work that is being done under this project that takes quite a lot of resources. And one of the outcomes that we're finally able to share with you, because of course it takes considerable amount of time to put something together. So finally we're able to share with you the leakage size databases, which Daniel will now present to you. So Daniel, the floor is yours. We might have some. Yeah, there you are.
Okay, thank you very much. So I just need to work out how to show the screen.
So while Daniel is looking for the presentation, let me just say a few words about him for those that do not know him yet. So he's a specialist in environmental performance and safety aspects of alternative refrigerants, especially with hydrocarbons. He's been working for GIZ Heat, UN agencies, manufacturers and end users, and he's also member of several standardization technical committees. So now I will stop sharing my screen so Daniel can take over. So you can click on the share button now, Daniel.
Okay. Right, okay. Can you see that?
Yes.
Okay, great. Okay, good day, everybody. What I want to present today is basically a summary of the databases, and in particular, focus on the leak size database. Just to provide a sort of overview, a sort of context of some of this work. This picture here is a sort of map of the contributing factors to the risk of ignition of a flammable refrigerant. And there's three sort of principal elements to this. One is the likelihood of a leak. Another is presence of potential ignition sources. And another is the size of the flammable volume arising from that leak. And what you can see here, there's the two contributing factors are the leak hole size and the internal conditions, the pressure, the temperature, and so forth, the phase of the refrigerant. And both of these basically dictate the mass flow rate of the release. And I should say those are also linked to some degree to the system tightness as well. Also, the developed concentrations in the event of a leak sort of are related to the size of the flammable volume. So the idea was to have two sets of data that can be drawn upon by manufacturers or other stakeholders to help improve requirements within safety standards, or to help provide input data to quantitative risk assessments. The two databases have been assembled from available information and placed obviously on the internet and the Lightfront internet site. The one that covers concentration data, that reports concentration data that was gathered whilst doing so-called leak simulation tests within a laboratory environment. So there's a variety of different types of equipment and enclosures, different mass flow rates, heights of releases, some with and without airflow, some with rooms that are congested and some that are completely empty, and so on and so forth. So there's a number of data sets there, and they can be accessed by this database. And as time goes by, we will populate it even further. However, the other database is excuse me, the refrigerant leak hole database. And this comprises data that we've gathered from the partners of this project and a couple of others. So this in itself presents the hole size that we determined, as well as all sorts of other characteristics associated with the system that they came from. And as I say, this is sort of the main focus of this presentation. Just to reiterate the issue, the choice of the correct leak hole size is essential for, let's say, optimized or wise handling and design of systems that use flammables. And this graph here, for example, shows on the x-axis the leak hole size, on the left y-axis the room area that's necessary to avoid a flammable concentration arising from, let's say, a flammable layer across the floor arising from the hole size that's listed, or on the right-hand side, the extent of the potentially flammable zone, or the zone 2 region within which you have to, or you should avoid positioning potential sources of ignition. So you can see that the choice of hole size, particularly in this sort of area up to around 2 square millimeters, is critical to get, or to use the correct hole size assumption. If you underestimate the hole size, then of course you underestimate the likelihood of a potential hazard. So it's likely that a flammable region could engulf a particular ignition source. But conversely, if you overestimate the hole size, then you similarly over-engineer the design of the equipment and expend too much money on essentially unnecessary protective measures. So it's sort of pretty critical to make sure that you select the right hole size. If you look at the various refrigeration, air conditioning, heat pump safety standards, there's a really wide variation in terms of assumed leak rate or equivalent hole size. And this graph here shows the variation of assumed mass flow leakage rate as a function of different standards and different clauses within standards. And you can see, so at one extreme, you've got this so-called 4-minute leak rate. And at the other end, you've got a leak rate that's a fraction of that. Yet the construction or the design of the equipment is potentially essentially the same. Some leak rates vary according to system charge, and other assumed leak rates are constant across the entire charge size range. And you know, this variation is sort of nonsensical and illogical, and it obviously results in potentially massively inconsistent designs and costs for mitigation. And I have an example here in the bottom right. So you've got a floor standing air conditioner, a so-called comfort cooling, and then on the right hand side you have coolers for data centers that aren't cooling people for human comfort. And you can see that the allowable refrigerant charge varies by an order of magnitude, by a factor of 10. And this just doesn't make any sense. So, and one of the reasons for such a wide variation is due to that assumption of leakage rates. So it's a fairly fundamental issue that needs to be resolved here. Okay, in terms of the project, we initiated a collection of lots of data. So not only under the EU Life Front project, but also under the GIZ C4 project, we aim to collect as many leak holes as possible and analyse them. Within the current database that you now have access to, there's about a little bit more than 250 samples, or okay, the data from those samples. And all of these samples are from in-use operation field samples. They're not specifically not from the production line, because obviously those holes will go back and be repaired. As I mentioned before, the intention is to provide good, robust data for use in standards and also risk assessments. Most of the equipment that this came from is relatively small, so split air conditioners, display cabinets, and heat pumps, domestic heat pumps. There were 7 manufacturers that contributed to this, and they obviously covered quite a wide range of models, so air to air, air to water, water to air, and so forth. Across all that data, the majority of the samples came from R290 systems, but a few also came from R410A, isobutane, and R404A. Obviously, you know, since all these refrigerants are broadly non-corrosive and don't react with the metals within the systems, the hole size shouldn't be influenced by the type of refrigerant, just, you know, sort of physical factors. When determining the hole size, what we did was, well, there were 2 different approaches. One was to use a digital mass flow meter, and another was to use analog. So we made up these so-called leak meters with the analog flow meters, and gave them to certain partners so that they could go into their workshop where, for example, they received the parts of the systems that have been returned due to leakage, and then physically do the measurement there. Then we have this mass flow meter in the laboratory, and then for the samples that's been sent to us, we then do those measurements. And then all of the associated data and information surrounding that leak are then logged. Using all that data, so the measured mass flow rate or volume flow rate, pressure, temperature, and the thermodynamic properties of that fluid, we put it into the classical formula for choked flow through an orifice, and then that enables us to determine the whole area. And as I mentioned, additional data was also recorded. So the location of the leaking part, was it inside or outside next to the compressor, so forth. What components was it, if it was, the system size, the charge, the normal capacity, and also the estimated cause or mechanism that led to that leak. And here's some initial results. So on the x-axis, there are hole size increments in 0.02 square millimeter sections, and on the y-axis, it is the probability of that hole size within the sample set. So the probability is the probability of that, of a given hole size increment or interval over the entire range of samples. What you can see is that at least 85% of hole sizes are less than 0.02 square millimeters. The largest leak hole, which I'll talk about in a moment, was about 1.1 square millimeter. In terms of the measurement, there's an uncertainty associated with these measurements, obviously. Those that used an analog, the analog flow meter, the uncertainty was around plus or minus 6%, whereas with the digital flow meter, it was well within 2%. I'd say the area of greatest uncertainty is where is the assumption of the discharge coefficient, which is, if I just go back to this part here, and there's a sort of standard discharge coefficient of 0.6, but actually it sort of depends on the shape and the geometry of the hole itself. 0.6 is generally the highest number, or okay, the fluids going through these holes. But what we did, in doing these calculations, we assumed a slightly lower discharge coefficient, which would lead to let's say, an exaggerated hole size, just to be on the safe side. But anyway, because of this range of possible discharge coefficients, then we're looking at an uncertainty of around, 15 to 20%. In terms of leak mass flow rate, again, I've got a similar plot here, and the values are based on a vapor pressure, saturated vapor pressure corresponding to 35 degrees C of R290. And again, the distribution looks pretty similar. You've got 90% of leaks that fall below a mass flow rate of around 3 grams per minute, and 95% of leaks are down below 10 grams per minute. I also just want to add that all the samples that we tested, they're ones that the manufacturer, when they either serviced the equipment or they were returned, showed a observable leak. But this probably only represents, I don't know, less than 1% of leaking systems. The majority of leaking systems emit in the order of, grams per day, grams per week, grams per month. And obviously these leaks are too small to observe, and certainly too small to measure with this equipment. So this this data set here only represents the section of the data with very large leak holes. There's one additional point here, and that is what we observed was that there's leaks that are due to technician intervention and leaks that are, I don't know, let's say naturally occurring. The majority of the leaks that we looked at that are associated with a technician intervention was quite small, but they also represent the largest holes that we found. So perhaps the largest hole was this one, which was about 1.1 square millimeter. and this was due to a technician repeatedly brazing the hole on a return bend on a evaporator. And what we wanted to do, okay, so they went and brazed it, and then they went back and brazed it, and went back and brazed it again. And obviously that just melts the metal. The hole got larger and larger and larger. Another one is in this example here on the right-hand side, where a technician had put his pipe cutters onto a filter dryer and obviously made a massive slit in it. So these holes that arose from technician intervention, we haven't included those in the final. Okay, we've got two analyses. One is with and one without technician intervention. But certainly for this case on the right-hand side, as soon as the technician makes that hole, he can't do anything else. He's got to cut the entire section out and put a new filter dryer in. If you try to charge the system with this hole, then the refrigerant's going to come out of the system just as quickly as he puts it in. So it'll never be operating by itself. So we realized it was important to make this distinction. I have a few more graphs here that show certain aspects. So one is how the age of the system affects the hole size. And you can sort of see a trend here, but I don't want to pin anything on that, because obviously all of the samples that we've had, they are within the warranty period of the equipment. And some companies have got longer warranty periods than others. So you tend to have a lot more data points within this sort of 1 to 2 year period rather than longer periods. And of course, you know, I think if you did this analysis on all systems that are in the market, then you'd probably end up with one of these sort of U-shaped distribution curves, because obviously as the system gets older, you have a lot of leaks once you put the system into operation, but then in 10, 15, 20 years time, as it reaches the end of its life, then the hole sizes begin to get larger. So this probably isn't really this probably doesn't give a fair impression, but I just wanted to show the graph. And then there's two other graphs. One is where the hole size is plotted against the system charge, the nominal charge of the system. And then down here, it's the hole size plotted against the system nominal capacity. That could be heating or it could be cooling. Again, this is just a snapshot, and you know the data is also limited in terms of the numbers of systems of different sizes. But still, I think it gives quite a useful indication, particularly in that, you know, previously, or in certain standards, there's an assumption that the entire charge leaks out in 4 minutes, and that's evidently nonsense, because if that was the case, then these larger systems, you'd have a curve that looks something like this. You'd have larger systems with larger leak holes and smaller systems with smaller leak holes. And that's obviously not the case. So I think it's quite useful to disprove that particular fallacy. Carrying out an initial statistical evaluation of this, basically we have a 99.9% confidence level that 95% of the leaks will not exceed a third of a square millimeter. And I think that is also a useful message. I mentioned before that all of these samples are of a size that were observable. If we try to put this in the wider context, we can take sort of average typical annual leak rates for these types of heat pumps, air conditioners, commercial refrigeration cabinets, and across the literature, this is in the order of around 5% per year of these types of systems that leak. From previous work, we found that leaks occurring with, let's say, more than 1 gram per minute represents perhaps about less than 1% of all of those leaks. So 1% of those 5% of leaks are within this sort of observable range. So that means that for those larger leaks, you're looking at something in the order of 3 times 10 to the minus 5 leaks per year. So that also is quite a useful finding for carrying out quantitative risk assessments. And we're hoping to sort of discretize this further into different sizes of leak holes. Now that we know what the leak hole size is, we can plug that into some calculations using whichever refrigerant you want to choose. So if we take this 1/3 of a square millimeter leak hole, then we can apply that to the mass flux of the given refrigerant, so in this case, say R290, and that gives us a range of leak mass flow rates for systems that are, say, operating at 15 degrees, saturated temperature 27 degrees, or 45 degrees, for example, for the high side of the system. And this then provides useful data for estimating the size of flammable volumes and so forth. So to come to the interim conclusions, probably a lot later than I should have done, these 2 databases have been made available on the LifeFront internet site, and there's one accompanying report available now, I think, and another will become available soon. The collection of the leak data is, I think it's really, really needed. There was one study a few years ago from Japan, which took about 20 leak samples, but that's quite small. Even 250 is relatively small given the number of systems and installations and variety of equipment that's in the field. But unfortunately, gathering this data is really tough, really time consuming. Of course, no manufacturers want to admit that their systems leak, and this is a major barrier. But it's essential for developing requirements based on real data, not from rumour, not from what the bloke told me in the pub last night. Oh yeah, I saw a hole that big. So far the results are useful and they're solid and they have a high level of confidence. But as I say, more data is useful, and we would very much welcome contributions from everybody that's participating in this seminar. Clearly, the vast majority of leaks are very small, and so-called catastrophic leaks are extremely rare. In fact, so far, well, I think we saw one that might be considered to be catastrophic. And then lastly, we see these databases offering a major benefits to the industry and stakeholders that are working on hydrocarbons and possibly other flammable refrigerants that are apparently not particularly flammable. So that concludes excuse me, my presentation, and I look forward to answering the questions that have been circulated.
Thank you very much, Daniel, for the extensive presentation, which was, I think, very insightful. Maybe just a quick follow-up question or a comment in case anybody would like to contribute with the data. Can you just briefly say how they should proceed?
So you're asking me?
Yes.
Sorry, can you ask again?
If you can just explain if anybody would like to contribute with their data to the database, what do they need to do?
Yeah, it's not as simple as we would have liked, but I think what we would like you to do is to contact us, one of us, and we will then provide you with the framework for how to do this. There's two options. One is that you cut out the parts of the equipment with leaks and send them to us, or if you have a lot, then we can send you one of these leak meters, and you can do it yourself in the workshop and then send us the data. But we can send you an input sheet so that you can put all the information in it.
Yes, we also have contacts on the website. If you go to livefront.eu, you will also find the contact details there. And I see that we have some questions coming in, but before we take the questions, I would like to still give the floor to two other speakers that we have lined up. The first one is LAURE MELJAC from NIBE. She has been with NIBE for 2 years, but she has been working in the heat pump sector for some time. Also as a researcher, she has a PhD, and currently she's in charge of a department monitoring EU regulation standards and certification. So NIBE is also one of the partners in this project, and they have been contributing. So Laura will share with us the experience of her company and the reasons for joining this effort, and also what she expects to see as outcome of this. So I will give the floor to Laura.
Yeah, thank you. So, okay, so I hope that everybody can see my screen. So good afternoon, everybody. So I'm trying to, yeah. So yes, I'm Laure MELJAC, so working at NIBE in the International Affairs Department. And so NIBE is a Swedish company focused on three main core businesses. So we have the NIBE Climate Solutions, mainly producing heat pump. We have NIBE Element producing components, and we have NIBE Stoves producing stoves, obviously. So we are active mainly in Europe and mainly in the Nordic countries, specifically in the Nordic countries, and we are also active in North America. So at NIBE, we have been working with flammable refrigerant for decades. So we have acquired a quite long experience in handling mainly R290. It is the reason why we have decided to join the LifeFront project. We hope and we believe that the LifeFront project can help removing the barriers to the usage of flammable refrigerant in the heat pump, refrigeration and air conditioning industry. So yeah, within the refrigeration, air conditioning and heat pump industry, it has been always needed to assess what is the leakage rate. For equipment using HFC, it is important to get to know the leakage rate in order to assess what are the CO2 emissions coming from the uncontrolled release of HFC in the atmosphere. And as far as equipment using flammable refrigerant are concerned, the knowledge about the leakage rate is important for safety issues. So as of today, the information that are publicly available on leakage rate and leak causes mainly come from theoretical assumptions and simulations, or lab researches, or broad estimation coming from the field, for example, from HFC data bank. But there is a lack of input from the industry for obvious confidential reasons. So today, there is a really limited available public information based on field experience. From the industry, so we have little information publicly available. Internally, of course, we all have built our own experience based mainly on the major failures that are reported to the after sales and quality department, so we are aware of the worst cases. Unfortunately, we have a very limited input on small leaks that are fixed on the field by installers. So we have limited input on which component leak and which are the leak rates. We have also, of course, experience coming from our technical departments on the causes. But again, what we are missing is what are the main cause for a leak to occur and what is the associated leak flow rate. So within the LIFEFRONT project, so there have been a collection and the collection is ongoing on samples coming from the field. So for each sample, there is quite a detailed data collection on the failed components, the leak cause, the leak hole size, and the leak flow rate. And so the added value for the industry of this leak database is that this database gives a statistical approach of the leak causes and the leak flow rate. And also from the database, it can be possible also to correlate the leak flow rate to the leak cause. And this is extremely beneficial, especially for the one that would like to use flammable refrigerant in heat pumps. Because knowing about the statistic of the leak cause and the leak flow rate really help to make the risk assessment. Knowing the leak cause help also improving the design of the product. And knowing about the flow rate can help defining a valuable method to evaluate the design efficiency in mitigating the risk related to the leakage of flammable refrigerant. So all in all, we think that the data collected within the LIFEFRONT project can be very helpful for developing products that have an appropriate design and that appropriately tested to ensure that to ensure a safe usage of flammable refrigerant. So we really believe that the database, but not only the database, the LIFEFRONT project altogether, can provide really valuable input to change the product safety standards and to increase the allowable charge of flammable refrigerant in our industry, so with refrigeration, air conditioning, and heat pump industry. So that's all for me. I give the floor back.
Thank you very much, Laura, for your input. So next up, we have Werner SCHWAIGER from AHT. So AHT is a manufacturer of commercial refrigeration cabinets using hydrocarbons, and Werner is a head of laboratory at AHT in Austria. As you can see, he has a long experience in developing, testing, and certifying commercial refrigeration appliances, and he's also a very active member of standardization committees. So he will also tell us from his experience as a partner in the LIFEFRONT project, what have been the contributions for his company and how he sees these databases will contribute to the standardization processes, especially in case of hydrocarbons. So I will give the floor to Werner.
Hello, thank you very much. Sorry for my speak. I'm a little bit, sick in the moment, but no problem. Welcome from my side. So AHT is working on the commercial refrigerating industry side and is a global player. And now AHT is also a big member of the Daikin group since this year. So we launched, so a huge thing is we launched the 100% environmentally friendly units in the year 2003. So we start our work with the hydrocarbons before the year 2000. And after that, we shared and collect experience with our partners on the ice cream side and different applications. And this is a very important for us, yeah, to work on the hydrocarbon side, because it's the future, as you know, from the refrigerant side. So we got 3 questions why we have decided to contribute to the database into this project. So for us, it's very important to share our experience and knowledge with the LifeFront project. So we have a lot of experience in the field, but we saw also here the information out of the field is very difficult. As Laura mentioned, it's difficult to get information from the field back. And so it's always good under the LifeFront project that you have maybe the focus on this topic also. So this helps to improve the products and also the service. So this was a decision. It's very helpful for the improvement of product and our service partners. And also important is the database for developing of our standards for the future and the current standards. So environmental sustainability is, yes, of course, very important, and also focus on this database. And we always, we take over actions and activities. So we are always working on this kind of projects to bring all together forward to the next step. So the next question comes up. Why it is important for the standardization process. So this is, databases are important for the standards. As Daniel mentioned before, since for some years ago, we had some discussion, what are the leak sizes, how big they are, what are the data, and we have only data from Japan. So this is all, like Daniel mentioned, so the LifeFront project helps really to get more data out of the really the live world in the field, to see, okay. And this is important to update all of our standards on every site. So like the standard -89 for the commercial refrigerators, also for the 378 or -40 standards for the heat pumps. So release conditions and mass flux rates comes out of this data, and this is also, yeah, a big input to get the feeling, is this the right way? Should we correct something? So this is also good to know what happens here. The values for different refrigerants. Yeah, of course, I saw here also a question about the different refrigerants. So this is also important to know. For the risk assessment, it's important to know, to have some data ready, and then you can make your calculation for the risk assessment. And also for our suppliers and for all of us to improve the parts for the future. So this is important. So the recommendations to you, why should you contribute with your data? So the experience, what you have, is also important for all of us. So it's good to know, okay, which experience do you have, and hide the data. It's good, yeah, to share the data what you have in a big database, so everybody can take a look where this leak comes and what is the consequence out of this. The bigger overview is the output of this data. So we have more data, a bigger overview, and different applications and systems. So if we have input from the different application systems, like I saw some questions from the field, how installation is working, putting in 150 gram inside and make a hole, what happens. So it's also useful for us, and we should create the values for the future because our planet is important, as we know. Yeah, so HD is always working on that side, and we are looking forward to fill up the database with fresh data and new data. Thanks.
Thank you very much, Werner. I think this call for action to other manufacturers is very important, and we've gone through an extensive exercise to reach out to relevant players in the market. And we've been faced with quite a bit of challenge because of the confidentiality, as it was mentioned. But I think we have been able to overcome this barrier, and we invite as many players as possible to contribute to this data collection. We have quite a few questions, so we will not really be able to answer all of them. But before we go in there, maybe some of you might be asking where you can actually see the databases. So let me just quickly show you. You go to the livefront.eu website /databases, or you can also see it in the menu. And you have the two databases next to each other. So when you click on the leak size database, for example, this will open up a page where you can see all the data points. So you can see what type of data is shared, and also the relevant information. You can also see the overview for the probability and leak flow rate. And you can also download the template to share your data if you are interested to contribute to this data collection. So now we can have a look at some of the questions. As I said, we will not be able to answer all of them, but please rest assured that we take all the questions seriously, all the contributions as well. And we will also get back to you in writing after this webinar. So one of the questions I see here, do you have correlation between refrigerant type and size of leak? So perhaps Daniel can quickly answer this one.
Not really. I mean, as you saw, the majority of the leak samples were with R290, but I also don't think, and I wouldn't expect to see any correlation, because what's the cause of the leak? Vibration, fatigue, corrosion, and so forth. And all of these causes are refrigerant independent. So I think that if you did try to find a correlation, you wouldn't find one. I think other factors are far more significant.
Okay. Then we have a next question, which is a bit longer, but let me read this out. Philip Johnson is asking, in my opinion, many of the refrigeration, AC and heat pump industry understand that the vast majority of refrigerant release events are due to very small leaks, perhaps on the order of 90 to 99% or more of releases that will not cause a significant flammability hazard. But safety standard must focus on the tail of the distribution, since dangerous situation occurring during 1 in 100 leaks is a high risk to society in aggregate when considering thousands or tens of thousands or hundreds of thousands installed units. How much data in the database will be needed to provide statistically valid data? So a question to Daniel, what do you think? Maybe this is something you've already been discussing with other players in the market. So what is it, when can we be confident that this is statistically valid? Is it already statistically valid, or do we need more data, and how much would that be?
Yeah, I mean, that question is the question that we posed at the beginning of this project. When when I talk to manufacturers, and they just say, no, our systems don't leak. We don't have any leaks. And if there are, they're so small you can't see them. But of course, that isn't very helpful. If I sit in a standards working group, certain people say, no, all systems leak, and a lot of the time they leak with a full pipe shear. But again, that can't be true because we don't see lots of systems leaking like that. So the truth is, or the fact of the matter is, somewhere in between these two wide boundaries. And so the purpose of this work, this project, was to try to pin down where we are, you know, what size of leaks are actually occurring, and where and when. And so you'll see in the reports that you know, we've tried to address this this question, and I think so far with the leak samples we've got, we have a very good statistical significance of the data. But as more leak samples get in or come in, that will be improved. And I have a box of holes that I still need to go through and add to the database, and hopefully we'll have many more as well.
Okay. So next question: to our experience, larger leaks occur on faulty sealings in automatic valves or loose threaded connections. Aren't this type of leaks included in the database, or they're included in other probable cause?
Well, I'd say that because of the types of equipment that we've been taking samples from, we don't have so many systems with automatic valves and threaded fittings, but nevertheless, all leaks that we find are logged, and so whatever's there is there.
Yeah. So next question: how to measure leakage mass flow in grams per minute or hours? So maybe something more practical. How do you measure leakage mass flow in grams per minute or hours?
Well, I think if you sort of refer back to the presentation, okay, you can see explained there's two means by which we measured the mass flow rate. One was a digital mass flow meter, and another was an analog. Yeah, that explains how we determined the mass flow rate under fixed pressure and temperature, and then we reduce that data down to hole size. So it's that's the easy bit of this project, I should say.
So based on a quantitative risk assessment, what is the most likely to happen with small refrigeration systems? Electrical fires or hydrocarbon fires?
I think the field data gives a very strong answer to that. Electrical fires occur in about 1 in 100,000 appliances, or 2 in 100,000 appliances, whereas fires due to leaking refrigerants are in the order of, you know, 1 in 10 million or 1 in 100 million per year. So electrical fires are far more likely to occur than ignition of leaks hydrocarbon.
Yeah, it's also the experience from the field. The statistic is what Daniel mentioned is valid here. So electrical fire the risk is higher than the refrigerant from hydrocarbon fire.
Okay, and then a question regarding the databases. Nicholas is wondering whether the databases will be available, downloadable in Excel or other formats. Daniel, is this something, as far as I know, we have not considered that for the moment, but of course that can be done maybe on a one-to-one basis.
Yeah, why not?
Yeah. Okay, and let's take one last question. Have you broken out leakage by fitting type or by installation type? A question again for Daniel.
Yeah, that's part of the project, and in fact, we wanted to develop or one of the objectives is to try to develop a correlation between components and leak frequency, as they do in other industries. But of course, we've got a lot of data and a lot of work to do, and that side of it will come next, hopefully.
Okay, very good. So we still have some questions that we couldn't really tackle during this webinar because we just have 1 hour allocated, but we will make sure we get back to you in writing. We will also follow up with recording and we will share the presentations. So you will be able to go back to the information that you heard during today's webinar. I think the last thing I would like to share with you is to invite you to a workshop during Atmosphere Europe conference, which is happening next Thursday. So for those of you who are attending Atmosphere Europe, feel free to join us for more discussions about the LifeFront databases and how you can contribute to the outcomes of this project. Join us for this workshop at 1:15 p.m. on Thursday. So with this, I would like to thank all the panelists. Thank you very much for all your contributions. Thank you all. Thank you also to the attendees, because I think you've been really active in asking lots of questions, sometimes tough questions as well, but that's, I think, necessary in this case. So in case you would like to follow up for more information, in case you're interested to contribute to the data collection, please feel free to reach out to us or to Daniel. We will make sure we follow up with you as soon as possible. Your inputs are very valuable, and we look forward to hearing from you all. So thank you again for listening today, and have a good rest of the day. Thank you. Bye-bye.